So the first thing we want to talk about is the electromagnetic spectrum. Now, of course, centuries and centuries ago, people have been studying the way that light travels. But it wasn't until Michael Faraday actually noticed that light responded to a magnetic field that we come up with the term electromagnetism. And of course, Michael Faraday is well known in RF circles because of the Faraday cage. So here is a definition of what we mean by electromagnetic radiation. Is the movement of electrically charged particles that create waves of energy, which are then referred to as electromagnetic radiation. Now, when we talk about electromagnetic waveforms, we talk about them in terms of the frequency that they operate at, the wavelength, and also the photon energy. Now, frequency and wavelength are actually inversely proportional, and so frequency equals the speed of light divided by the wavelength. And we talk about frequencies when we talk about radio waves. So when we're down at the lower end of the frequency and we're talking microwave, radio, TV, long waves, we tend to talk in terms of frequencies. How up at the higher frequency levels, when we're talking about gamma rays and X-rays, ultraviolet, visible, infrared, then what we tend to talk about is in terms of wavelengths, but they're actually related. So the higher the frequency, the smaller the wavelength. The lower the frequency, the greater the wavelength. So the photon energy is actually proportional to the frequency, and so up at the very, very high frequencies, you actually have the most energy. So something like the gamma ray can have energy of like 1 billion electron volts, whereas when we come down the frequency, the radio waves have a lot lower energy, and we start talking about a femto electrovolt. So the main thing you need to understand from this slide is electromagnetic energy has a very, very wide range from the very high frequencies to the lower frequencies. And in this slide here, you can see the visible light, and that we can actually see. But radio waves at a much lower frequency, we can't physically see, but they're there. And that's what we're going to use to be sending our ones and zeros over the air. Now on this slide we're going to look at the classes of electromagnetic radiation. And what does that mean? Well, they're classes of usage. Different regions of the spectrum are used in different ways. And again, what we're interested in is this group here called the radio waves. And you can see AM radio, for instance, the wavelength is over 1,000 meters. And so that can actually travel quite far, and the wavelengths are very, very long. As you go up the spectrum and you start getting in to the microwave, you can start to see that the wavelength is about 10 centimeters. Now, why is that important? Is because the way that those waveforms react when they hit obstacles such as walls, your body, your car, will depend on the wavelength. And so understanding the frequency that you're operating on is very important for understanding the effect that frequency has and those waveforms have on the coverage that you're going to experience. In a little while you're going to see that for wireless LANs they operate in a frequency which has a wavelength which is probably less than the size of your hand. And so we're going to build up to understanding that, and again how that bounces off walls, etc., is dependent on what the wavelength is, and also your antenna design will also vary depending on the wavelength of the frequency that you're using to transmit. So it can be hard to visualize what radio waves are doing, and so here we're just going to go through some of those characteristics. First, the electromagnetic radiation is constantly moving. It travels at the speed of light, which is 3 times 10 to the 8 meters per second. So it's constantly moving. So they do not possess any physical mass. In fact, the term radiation simply means the energy that's being transmitted by waveforms. They do not possess a charge, and they do not require any medium to travel from one point to another. And the interesting thing about radiation is that as it moves and goes through walls and glass and other obstacles, the speed may slow down, but the frequency doesn't change, so it still continues to operate at the same frequency. So when you think about the receiver, as long as you're able to receive on that frequency, you're able to receive that signal. They are subject to the normal laws of reflection and refraction. They can also be absorbed by matter. So just like you feel the heat of the sun on your body and your body absorbs that heat, so it is with electromagnetic radiation, it can be absorbed by different types of matter. And the last one is super important for you to remember. The higher the frequency, the shorter the distance the signals can travel, which conversely means the lower the frequency, the greater the distance can travel.